morning, ladies and gentlemen. Welcome here at the Technical Forum at the group exhibit Hydrogen, Fuel Cells and Batteries. Welcome you here at Hanover Fair 2016. Our partner country this year are the United States of America. And for that, I feel honored to present to you our first speaker from the United States representing Precision Combustion. We'll hear the representative of Research and Engineering. And for that, please welcome with me on stage, already here, Mr. Roychoudhury. Okay, thank you.
Hey, Thomas. I feel like a rock star already. Good morning, ladies and gentlemen. Today I'll talk about reformers that we have progressed over the last few years, and a little bit about the hydrogen and syngas generation aspects of it. So with me is Tony Anderson. He's back there in our booth, which is D33. And PCI, we are located in North Haven, Connecticut. We're about a 40,000 square foot facility. We make catalytic reactors and catalytic combustors. Reforming is one of the main areas that we work in. That includes everything from syngas generation to hydrogen generation for chemicals purposes, from small watts to megawatt scales. We also do a lot of work on sorption. These are for biochemical contaminants, for sulfur removal, and for trace contaminants. Generators. For small portable generators, we have 1 kilowatt and 400 watt generators that we make that are based upon mostly internal combustion engine generators, but they are diesel generators that are small portable units, and we work on unmanned aerial vehicle units. Large combustors, gas turbines, burners for oil exploration, downhole steam generation, Stirling engine burners, and so on. And where we are now is we've made prototypes of several of these pieces, and they're in the field or testing, advanced prototypes. We do the controls, the packaging, and that's the core of our business. We were established in '86. We're privately held. We have about 34 folks. And our collaborators include the US government, small and large corporations, universities, national labs. So, there's a range of stuff that we work in. They range everything from fuel cell systems, IC engine gensets, UAVs, drones, and so on and so forth, reformers for industrial systems, various combustion systems, air cleaning systems, and there's a lot of other stuff from Sabatier, methanation, chemicals manufacture, and so on and so forth. So today I'll focus on the reforming aspect of it. We're active in the major areas of reforming, what we define as catalytic partial oxidation, where there's just fuel and air, there's no water. Autothermal reforming, again catalytic, where there's fuel, air, and some water. And steam reforming, which is mostly fuel and steam. And so we have products in all these areas. I will focus today on just these catalytic thermal reformer concept and where we have taken it, because we find an opportunity with SOFCs that seem to fit the bill here very well. We also work on hydrogen purification for PEM systems and hydrogen HT-PEM systems with water gas shift and proc systems, and of course for hydrogen generation via membrane separation. Okay, so the microlith technology, it's essentially a coated mesh type material, and there's a close-up of one of the strands of the mesh, and again you can see the catalytic coating versus the metal coating, and it's very important to have very good adhesion and cohesion between these metals so that they don't spall off. We make them in an automated process, and then we use it for reactor development. We have multiple patents on catalyst structure, the reaction methods, and apparatus, but we have no patents on our coating process because that's the proprietary part of it. Okay, so today we'll talk about the simplified system layout for the fuel cell APU. This is something that we have developed and tested, and I'll talk a little bit about it. So the first component is the reformer desulfurizer. So it takes in any jet fuels, gaseous fuels, liquid fuels, and it reforms it. If you need to desulfurize it, it has a sulfur sorption bed within it. It sends it to the fuel cell, and from the fuel cell, the residue goes to the burner. So we don't make the fuel cell. We make all the other components that go around it, and the thermal balance, the burners, the controls, and so on. So I'll talk a little bit about some of the demonstrations we've done on this, and most importantly, these systems are water neutral. So these reformers we've done from a range of reformers, everything from 100 watts, which we call wearable systems, to 1 kilowatt, to multi-megawatt systems. They range in size from little pocket-held devices to very large systems. Specifically today, I wanted to talk about a 1 kilowatt diesel jet fuel reformer desulfurizer. So this can take any kind of fuel, liquid fuel, with up to 3,000 ppm sulfur, and be able to run solid oxide fuel cells. This is a desktop PC box cabinet, if you will, and this is the inside of the cabinet. We've got the reformer desulfurizer components up there. We have all the balance of plant components in here, the controls up front, the fuel tank, the water tank, the water recovery, those kind of components are all packaged within it. So it looks pretty much like this device. You turn it on, you turn it off, and then you can control if you're sending it to a solid oxide fuel cell, whether you want 300 watts or 1 kilowatt, you can control, or you can have interface with the stack controller. And we've run it with these, with solid oxide fuel cells along those lines. So it's a fully packaged 1 kilowatt fuel reformer system, including sulfur cleanup. Includes all balance of plant components, pumps, blowers, controls. It's capable of standalone facility independent operation. Pretty much we run it with a stack directly, but for startup, for instance, you'll need power, so whether you use a battery or electrical power. And includes safety interconnects and stack interface control. So the stack will have different requirements for startup, shutdown, transients, so on and so forth. Pressure drops, temperatures, and those are managed within this system. Just to focus on the transition, about 5 or 6 years ago, we were building carts. Then we started building standalone systems, and finally we've transitioned to single dedicated control boards with package systems. Here's some data with a 1 kilowatt fuel cell test. IV maps and so on and so forth. So essentially the reformer connected to a stack, and we've connected multiple stacks from different different manufacturers that we've used. So this is, in particular, was a 1 kilowatt system with 3 kilowatts thermal reformer with all BOP components and desulfurizer. 1 kilowatt SOFC, and this is the efficiency was 25%. Again, at an early stage without optimization, that was the efficiency that the system received, the system output was. Again, this all depends upon fuel utilization within the stack capacity, and so on and so forth. We ran it for about 500 hours with jet fuels with several hundred ppm sulfur and stable operation. And we've operated the reformer itself for about 1,500 hours on jet fuels containing up to 3,000 ppm sulfur. So the key is that the reformate going into the stack has to be less than 50 ppm hydrocarbon, much less than 1 ppm of sulfur, probably in the ppb range. And the temperatures have to be consistent with what the stack is comfortable operating at. Here are some compositions for something operated with a 400 ppm jet fuel. So something you take right off the flight line, for instance. And the compositions for that 1 kilowatt unit, 1 kilowatt electrical at 3 kilowatts thermal, 1.5 kilowatts thermal. So you're looking at the turn down, and you look at the hydrogen composition, the CO composition, the C2s, the C3s, And in general, what you're seeing is you're getting almost complete fuel conversion, and your lower heating value reforming efficiency is about 80%. And the reforming efficiency is based upon caloric value of the fuel coming in to the caloric value of the fuel exiting. And key important thing is less than 50 ppm higher hydrocarbon, and much less than 1 ppm, probably in the ppb range of sulfur going through. So we've got a mock-up of this device, of this 1 kilowatt unit in our booth at D33. And so what it includes the ATR, the fuel injector, the steam generator, the heat exchangers, desulfurizers, sensors, controls, pumps, and the blowers. Everything needed for driving the reformate into the stack. It weighs about 10 kilograms today without much optimization. The case itself weighs probably about 2 to 3 kilograms. And we've tested it with various fuels, diesels, jet fuels. We've confirmed operation with up to 3,000 ppm sulfur. It's important, 3,000 ppm sulfur is an important number because that's the spec number for some jet fuels, and we have to qualify it to the spec value of the fuel. And it's important that even at 3,000 ppm, we don't get unburned hydrocarbons or sulfur breakthrough at those points. So sulfur cleanup to much less than half a ppm. It's a non-regenerable sulfur trap, but it has a high capacity. And so the capacity, for instance, is a 200 cc trap is good for about 3,000 hours with the ultra-low sulfur diesel that you get in the US, which is 15 ppm sulfur. In Europe, it's higher, so the lifetime would be a little different. But that's what we're in tests, that's what we're seeing. We run it to 1,500 hours without failure, with up to 3,000 ppm sulfur fuel. And again, at 1,500 hours, the way we look at performance is higher hydrocarbon breakthrough. And it seems fairly stable for most of the 1,500 hours. Oops, other way. Okay, so the other components that we've done is we've scaled it up to larger reformers. You know, this is a 2 kilowatt electric or about 5 kilowatts thermal. We've done dual fuel burners. These burners have integrated heat exchangers, so they can run on liquid fuel to start up and then anode exhaust later on. And the heat exchangers then are designed to operate such that it keeps up with the stack requirements. So if you're looking for a certain temperature rise per time or delta T, whatever it is, at pressure drop, those heat exchangers are built into the burner such that it can feed the SOFC directly and comply with the requirements for those systems. So we've run it with this 2 kilowatt system. We've run for about 270 hours with jet fuels and diesel. Again, electrical efficiency, this is net electrical efficiency of 25%, again, without trying to super optimize the stack or the system. Here's some data. Standard data, 125 hours, another 125 hours with this operating, temperatures, stable temperatures, stack voltage, power output. There was a shutdown in one of the cases. The previous data was with diesel, tier 2 diesel, and the second data was with 100 to 400 ppm sulfur jet fuels. And again, there was a shutdown at a certain point and came back to right where it was. But it's fairly stable if you can manage the temperatures, the thermal gradients. The stack seems fairly stable. And that's a close-up of the burner. This particular one is about an 8 kilowatt burner, weighs about 1 kilogram and about 1 liter size. And it's a dual fuel, has its own startup, can run on anode exhaust or on liquid fuels. So, in summary, what we have demonstrated so far is a packaged reformer system with about 80% efficiency. It's a simple approach for reformation and desulfurization. It includes all the BOP components and packaging and shows a path towards making a unified system. The burner, we've looked at dual fuel burners with water recovery systems that seem to be working. And just on closing, these were what we were doing before. We were working on test carts to enable testing. Some of the other stuff we were doing on fuel cells, IC engines, and Stirling engines. some of the larger stuff at the larger reformer sizes, the 5 megawatt sizes, some of the standalone systems on oxygen-blown syngas generators, for instance, that are being used industry, steam reforming with diesel, natural gas, and hydrogen separation for high-purity hydrogen. And the last item is a Sabatier methanation reactor, things that we've been working with NASA for. These things have been running for thousands of hours. Again, the key idea is to use CO2 to make something that's valuable. And please see us at booth 33. I'll take any questions if you have any.
Thank you very much. Mr. Roychoudhury is open for question. Are there any questions here from the audience at this time?
Subir, thank you very much for Rena's presentation. I have a question about capacity of your reformer regarding absorption. Do you have some regeneration strategy, or is it for some thousands of hours of work and then it should be replaced? What is your strategy?
So in terms of, we have looked at regenerated solutions. The complexity of the regenerable solutions, it can be done, but the complexity is such that it requires bed switching and so on and so forth. And so some of these applications don't necessarily lend well to that. So if you can take a very high capacity sorbent, again, the challenge with high capacity sorbents are not generally regenerable, because if you're regenerable, the capacity generally goes down. And so we've found that the best option is to use a inexpensive high capacity sorbent and make sure it's not a hazardous waste and be able to toss it and throw it away. That seems to be, but the key is, how do you know when it's saturated?
That was a very good question. All other questions can be taken to the booth. Once again, it's D33. And Mr. Roychoudhury will be welcoming you there and answering all the questions. Once again, thank you very much. Big hands, please. This was our first topic here in the technical forum. We kicked off, and the next topic will be the challenges of metallic bipolar plates, and that will be in 5 minutes' time. Thank you.